Greetings, everyone. My name is Aaron Gallant, and I'm an assistant professor of geotechnical engineering at University of Maine. Today, I'll be presenting on column-supported embankments, or CSEs, a ground improvement method that has been adopted by many transportation agencies in the United States and abroad to facilitate accelerated embankment construction. The installation of columns, which has been considered ground improvement, has become increasingly popular over the last 10 to 15 years, especially the use of unreinforced grouted or concrete elements with limited bending resistance. And while we have a great understanding of the vertical load transfer mechanisms associated with CSEs, the durability and lateral stability of these systems remains a salient concern, okay? And this study was motivated in part by a push to begin codifying design of these systems. And one consideration is to limit column spacing to prevent any cracking or fracturing, which may preclude designs that have otherwise proven to perform well. So the topic of today's presentation is on the lateral spreading and stability of embankments supported on unreinforced fractured columns over soft soils. And before I move on, I would like to acknowledge the hard work of the graduate student at UMaine, Neil Otero Lopez. The primary function of the columns is to reduce the stresses imposed on the foundation soils underlying the embankment. And as shown in the top left corner, columns are typically arranged in a rectangular or triangular grid arrangement to achieve a desired area replacement ratio and stress reduction, okay? Rigid elements are typically installed with a drill displacement tool shown in the top right, whereby a cavity is formed and the column is cast by injecting grout as the tool is withdrawn from the hole. But if I could focus your attention to the base of the embankment in this conceptual image, some settlement occurs between the columns as the embankment is constructed. This mobilizes the shear strength of soil in the overlying embankment and an arching mechanism that transfers the weight of the fill to the underlying columns and then to a more competent bearing layer at depth. However, it's important to recognize that some of this load is still shared by the foundation soils, particularly at shallow depths. Thus, there is unbalanced load in the foundation materials near the perimeter of the CSE system. So unbalanced loads can lead to excessive lateral spreading and basal instability of CSEs. But what we are particularly interested in answering is whether or not column yielding and fracturing necessarily exacerbate the issue. Now, rigid concrete columns are several orders of magnitude stiffer than the foundation materials, and this precludes mobilization of any lateral bending resistance in the columns and passive resistance in the foundation soil simultaneously. Therefore, if I focus your attention to the top image, we anticipate column cracking or yielding near the perimeter of the columns as the embankment is constructed and the fill height increases. However, if the columns are able to transfer the load vertically such that the foundation soils are not overstressed, the system will remain stable. If the foundation soils yield such that excessive lateral spreading occurs, column rotation and separation may lead to a cessation of the intended load transfer mechanisms and attendant basal instability. Okay, and this is illustrated in the powerful images below where we see bulging at the toe of the embankment and column yielding and rotation once the elements were exposed for this failed CSE system. So to further address this issue, what we did was we performed 3D finite element analysis, which can provide insight into the role of column fracturing, among other things, on vertical load transfer and lateral spreading. So below, I'm showing the half-cell geometry of a column-supported embankment that we considered in our models, where the elements are embedded in a competent bearing layer, which is overlain by a soft clay and a superficial layer of stiffer, over-consolidated clay. This particular phase of the study was intended to investigate three things. The first being the influence of area replacement associated with column spacing. The second was the relative thickness of a stiffer or stronger, over-consolidated superficial layer that often exists in many soft soil profiles, okay, and helps confine the system. And the third thing was the influence of yielding and fracturing, okay? And to simulate column cracking and the loss of tensile resistance, we adopted a discrete crack method whereby we introduced interface elements through the column at locations where cracking was predicted. And this allowed column rotation and separation for larger deformations. And though this method does neglect the energy release rate due to microcracking and fracture propagation at smaller deformations, it adequately introduces a constituent response to assess the global behavior of a CSE system on fractured elements. So what we've found here is that progressive cracking during filling does not necessarily reduce the efficacy of the column-supported system with regards to vertical load transfer and stress reduction on the foundation soils. If you look at the top image, we're illustrating the predicted sequence of column cracking throughout embankment construction to a fill height of 5 meters for this particular scenario. The red symbols that I'm showing here illustrate the location where yielding was predicted. And the numbers indicate when column yielding was predicted and an interface element was activated during the simulation, okay? The fill height, column location, and depth are all summarized to the right, but generally cracking initiates at the perimeter column where axial loads are lowest and then propagates behind the toe to the trailing columns. And in some cases, a second crack at shallower depths is predicted as filling increases. I'll just note that we've dubbed this a progressive crack analysis. Okay, in figures B and C below, we're illustrating the change in the maximum tensile stress in the perimeter column, okay, which we've normalized by the modulus of rupture, okay, when an interface element is introduced, okay, and this happened at different points during that filling sequence. But focusing now on part D in the bottom right, we're showing the axial load in the 3 columns located closest to the toe of the embankment beneath the slope, okay? And I'll note that one in this sequence was when the fill height was already 2.5 meters, and the thickness of fill over these elements did not increase over these particular elements, okay? And what we observe is that there's not a significant change in the axial load predicted in each column, indicating that the system is still able to transfer load to fractured elements and reduce stress on the foundation soils. Now, for the same embankment geometry shown in the previous slide, I'm now showing the distribution of lateral movements at depth near the toe of the embankment, okay, where we anticipate lateral spreading. And these are a proxy for stresses imposed on the foundation soils at this location. And figures A and B are the predicted deformations for drained and undrained conditions for different fill heights. And given larger deformations arise from undrained analysis, this is a less favorable condition and expected. However, what is not easy to distinguish are the 3 different curves associated with different column assumptions and different analyses. One analysis was performed where the columns were assumed to have an infinite bending stiffness by using a linear elastic material in the column, okay, which is the light gray line that we've called no cracks, okay. We're also showing computer results for a progressive crack analysis, again described in the previous slide. And the black lines are the predicted deformations when fractures or interface elements were introduced every meter at depth prior to simulating stage filling. So thus all columns were assumed to have yielded, and this is of course a more extreme condition. And we have called this an all cracks analysis, okay? So as you can see, there's no appreciable difference in the computer response, and column fracturing has no appreciable influence on load transferred and resisted by the foundation materials in this load sharing system. So another thing that we found, though, is that the thickness of the stiff superficial layer up top, okay, considered in these analyses has a significant influence on the predicted lateral spreading, all right? If you focus your attention to the top left image, I'm referring, to the dark gray layer, which we have noted has a thickness H1. And the 3 plots below, we're showing the predicted maximum horizontal displacements in the foundation soils at the toe, okay, which have been normalized by the embankment height. On the horizontal axis, we're showing the relative thickness of that stiff superficial layer, which again is normalized by the embankment height. And these computed results came from analyses where cracks were imposed every meter at depth through all columns, or the more extreme all cracks assumption. So now these plots are the product of more than 100 3D finite element analyses. So allow me to unpack them a little bit further. We're showing the range of computer results for undrained conditions, which is the light shaded region, while the darker gray region is for drained conditions, okay? And there is some overlap. And this overlap arises from different area replacement ratios that we considered, which range between 3.1 and 8.7%, typical for embankments supported on these elements. And the black symbols are documented observations from inclinometer measurements near the toe of CSE systems. So these are actual documented movements or deformations from full-scale CSE. Okay. The 3 figures vary only in that the soft soil conditions considered or simulated differ, okay? Where SC1, shown to the left, was calibrated to be the softest soil condition, and SC3 to the right was less compressible and stronger, and SC2 was somewhere in between. But for the New England geotechnical engineers in the audience, SC2 and SC3 are more akin to materials like Zumsprop Formation in Maine or Boston Blue Clay. And one thing that immediately jumps out is that the documented observations are in better agreement with the drain simulations, which suggests that CSE construction is closer to a drain condition. And I'll also note that soft soil conditions for the documented case histories are similar to SC2 and SC3 soil types, again, which are in better agreement with the computer results. Now, the magnitude and depth of stresses imposed on the soft foundation soils is limited by arching in the fill, as well as down drag associated with soil column interface friction along the elements, okay? And because stresses in the foundation materials are reduced and concentrated near the surface due to these hang-up effects, the drainage distance associated with excess pore water pressure dissipation is also much shorter, okay? So this drain condition, okay, is supported by, our own investigations, including in the field and numerically, as well as, consolidation settlements and pore water pressure measurements in soft soils reported by others for these systems. Okay? So while, CSE construction is accelerated and there's no significant delay period or holding period, it is likely closer to the drain condition. The final thing that I would like to address in these figures is that there's a threshold thickness of the surfacial layer, which is associated with the soft soil type and area replacement ratio, where the incremental rate of maximum lateral deformations increase with decreasing thickness of the surfacial layer, okay? So as this decreases, we see that there's eventually a threshold where we begin to see an increase in the deformation rate, and this generally corresponds to normalized deformations of approximately 0.5%, as well as the maximum deformations that have been observed from independent studies, okay? If I focus your attention to the top right, this increase in the rate of deformation with decreasing thickness of the stiff surfacial layer coincides with full mobilization of passive resistance or shear strength in that shallow layer, okay? Which I'm illustrating by showing the relative shear strength mobilized in the soil at this condition. Now, if the stiffer surfacial layer yields and offers no further confinement at shallow depths, significant column rotation separation in the trailing columns, could lead to an appreciable redistribution of stress in the foundation soils at basal instability. And a practical design objective would be to achieve area replacement ratios that achieve an acceptable amount of mobilized shear strength and lateral spreading, okay, which does not necessarily preclude column yielding or fracturing based on our numerical analysis. A final thing here that I would like to touch on is the influence of tensile resistance provided by geosynthetic reinforcement, which has often been installed at the base of many CSE systems. For the same embankment geometry discussed in previous slides, I'm showing again the maximum normalized deformations at the toe when geosynthetic stiffness, or when geosynthetics were considered, okay? For both drained and undrained conditions. I'm showing the geosynthetic stiffness along the horizontal axis, okay? Focus on here in the bottom right figure, all right? And while I'm showing both drained and undrained conditions, I'll focus your attention to the dark black lines for drained conditions for reasons previously mentioned, okay? And the symbols are observed deformations for cases where geosynthetic reinforcement was installed. And as we can see, based on the numerical predictions, the geosynthetic does little to reduce deformations for the practical range of geosynthetic stiffnesses considered. If I focus your attention to these case ID numbers 7.2 and 7.3, which are observations from the same test embankment and soil conditions, the geosynthetic stiffness had no influence, okay? And so this kind of corroborates our finding. In the figure to the right, we're further illustrating this point with a measure of geosynthetic efficacy, okay, which we define as 1 minus the ratio of predicted deformations with geosynthetic reinforcement, okay, over predicted deformations without reinforcement at the base of the embankment, where a value of 1 would suggest the geosynthetic stiffness eliminated any movements and 0 suggests it had no influence. So in closing, we studied the lateral spreading of column supported systems on fractured concrete elements, focusing on area replacement ratios typically utilized for these systems, okay, which also typically have maximum normalized deformations less than approximately 0.5% and agree well with our predictions and lend merit to our computed results, okay. We have demonstrated that column yielding and fracturing does not necessarily reduce the efficacy of the CSE system to transfer load to the columns, okay? Nor does it necessarily exacerbate lateral spreading, okay? So based on our study, we believe industry should subscribe to criteria where area replacement ratios are designed to achieve tolerable deformations and associated mobilization of passive resistance in the soil, particularly at shallow depths where the soil is often comprised of a stiffer, over-consolidated clay or denser fill than the underlying softer foundation soils. Ignoring the benefits of this material may lead to overly conservative designs, all right? And furthermore, subscribing to criteria that precludes yielding of brittle, unreinforced concrete columns will lead to more costly and less efficient designs that have otherwise proven to perform well in appropriate soil conditions. So I want to thank you all for attending today's conference and this presentation. I also want to acknowledge the financial support from the Deep Foundations Institute for this effort, as well as additional support from the Transportation Infrastructure Durability Center at University of Maine. And with that, I'll be happy to answer any questions.